Okay, welcome to last period. Today is the last chemistry lecture of honors chemistry.
No, it just means we're close to summer.
We're very close to summer. We have one lab after this where you're going to take stuff that you've already learned and apply it. Maybe practice a little bit of stoichiometry. That'll come back. Not hard. Then we have our quiz for you guys. It's on Friday.
What? This Friday? I won't be here. I'll be taking my AP exam.
Speaking of things like AP exams, I recognize that this is an honors class and a bunch of you are going to be in and out for various things towards the end of the year. So we'll just be real flexible with figuring out how to make things up. If you're not here for the lab, then we probably won't need to make it up, although you'll want to at least come by and see what's going on. If you're not here for the quiz, you definitely need to make it up. Then we're making soap. Then we still have our 2 review days. The other nice thing about those review days is if you have stuff that you need to make up, doing it during class on one of those days is super reasonable. Basically, my only timeline for finishing all the things that all of us need to finish is let's get it all done before the final. Yes?
Will we have a review for the quiz?
Probably.
Oh,
Well, so before I leave today, you will have a review for the final, which will include some acid-based stuff. I want to make a review for the quiz, but I definitely won't have it to you today. So,
even if it's like a day before.
yeah, just like something is a good goal. Quiz review. Boom. Okay, looking through the stuff. Number 1 says final review today. I already said that out loud. I always make my reviews really long because I like them to be thorough. And in addition, not in addition. So as a result, I made the final review really long as well. It's units 5 through 6. That's going to show up in your OneNote. Sorry, 5 through 8. That's going to show up in your OneNote before I leave today. I have it done. I just need to check the formatting and stuff. The review will show up sometime throughout the next week as I get it done, so that you have lots of time to check your answers as you work through stuff. As always, the review is not for a grade. Do it or not, I don't care. That's up to you. If you just want to study the key when I post it in a couple of days, that's fine with me too. If you want to go through and work on the ones that seem hard, whatever. Generally, most of what I did was copy and paste your original test reviews into one big super document, although sometimes I removed things if they definitely won't show up on the final. So that'll be something for you to look at. Your test grades. So those are in Backpack as of lunchtime today. So you can go look at the Unit 7 test. Most people did really well on it. Hooray, I'm proud of you. The way that always works is if you missed any questions at all, you are allowed to do corrections. As far as the timeline, we're all really busy. Just find a way to do those corrections between now and the final. So you have to do it by the 21st would be when you need it done. Because that Unit 7 test was, I guess it's not the last test because you have the acid-base quiz, but if anyone happened to make less than an 80 and you haven't already done a retest, remember that you can retest for up to an 80. And for that, I also just make that decision between now and the final. There are official rules about what you're allowed to retest. So you can't go back into the gradebook and be like, oh, last semester I made less than an 80 on something. I'm going to be more flexible with these last 2. So I suppose you could wait and see how the acid one goes and decide if you want to use your retest on that or this. But whatever, everything is just about preparing for the final as that approaches. Any questions on any of that stuff? Okay, let's jump into the homework. The first half of it is just notes, so we don't need to go over that unless you have any really specific questions about stuff that I went over in the notes. Paste. Was there anything where you thought, I'd like him to spend more time talking about that? As I slowly scroll through, pH, anything about that where you thought, I need clarity? How pH is calculated. I realized in this lesson I didn't reassert what makes something or how you decide something is an acid or a base. I just made you go back into the old notes. The way pH works is because of the equilibrium business, water naturally has 1 times 10 to the negative 7 hydronium and 1 times 10 to the negative 7 hydroxide. If I add more hydronium to it, that hydronium will react with the hydroxide a little bit and make it actually go down. So adding acid to water both increases hydronium and decreases hydroxide. If you do the reverse, if I add hydroxide, it increases hydroxide and decreases hydronium. As a result of that, if I put the concentrations of hydronium and hydroxide together, I always get 1 times 10 to the negative 14. And so when you throw a negative logarithm onto that to turn it into the pH scale, pH plus POH always equals 14. And that's where that middle equation comes from. pH plus POH always equals 14. Here are the math problems. Zooming in, especially because I need to redo number 5 still. I solved for the harder thing on number 5 instead of the thing it actually asked for, so I have to correct that. For numbers 1 and 2, you're just plugging in the concentration into the negative log formula. The way we do sig figs with scientific notation is you just count what comes before the multiplication sign. So numbers 1 and 2 have 2 sig figs because 2.3 has 2 sig figs, 5.0 has 2 sig figs. So for number 1, you should have gotten a pH of 3.6, which is less than 7, which is called an acid. For number 2, you should have gotten a pH of 8.3, which is greater than 7, which makes that a base. For number 3, I give you the POH and ask for the pH. POH plus pH always equals 14, so you just do 14 minus the POH. You get a pH of 1.7, which is less than 7, which makes that an acid. I'm going to delete that because it's not very helpful. For number 4, you have to do 2 steps. I give you the concentration of hydroxide and ask you for the pH. If I plug this concentration into a negative logarithm, I'm not finding the pH, I'm finding the POH, which in this case is about 10. Because pH plus POH always equals 14, 14 minus 10 equals 4. A pH of 4 is less than 7, and so that makes this an acid. Because of the auto-ionization of water, hydronium and hydroxide concentrations always work together. So you should be able to get from any pH, POH, or any concentration and get to any other point by just sort of mathing around. And then the last one, I solved for something way harder than what it asked for. Here's what you would actually do. This says, what is the concentration of hydronium if the pH equals 2.4? pH equals 2.4. That means the negative logarithm of the concentration of hydronium equals 2.4. So your 2 options here are to scroll up and look at the equation that I gave for solving these backwards. The other thing you can do is algebra. I'm going to do the algebra. If you want to just scroll up, that's fine too. Step 1 is to deal with that negative by multiplying both sides by -1. Negative 2.4. The next step is to recognize that a logarithm that doesn't have a written base is always assumed to be 10. And then we can do our little spiral thing to get 10 to the power of -2.4 equals the concentration we're looking for. grab a calculator. 10 to the power of 2.4 negative equals 0.00398. 0.00398 with 2 sig figs, that would be 0.0040. Or if we wanted to write it in scientific notation like we normally do, 1, 2, 3, 4.0 times 10 to the negative third molar is the concentration of hydronium. To go backwards, pH or POH, it's always just going to be 10 to the negative pH or 10 to the negative POH. So if you memorize that, or if I'll just give you all these equations again, you won't need to do logarithm spiral stuff. We'll save that for half-lives. And just 10 raised to the power of whatever. Yes?
So I forgot to do negative 10 on all my logs. So I got
Was it just you have a negative instead of a positive?
I just like put in front of the logs. I just didn't include the negative at all.
Uh-huh. I mean, wouldn't that give you the same answer but negative?
I don't know. I'll look at the key. I'll look at it later.
So like, did you get negative 3.6 for number 1?
No, I got negative 8.3, 8.4.
Are you looking at number 2?
That's what I thought. But then on number 2, I got negative 19.
So what you want to do is just make sure that you can figure out how to make a calculator tell you 3.6 for number 1. Yeah. Yeah.
So could we leave the concentration as like constant for like the last question, like the brackets, like the step above the one that you squared, like the brackets equals 10 to the negative 2 step back. Could we leave it as that, or should we just like evaluate the 10?
No, I want you to evaluate it. Yeah.
Okay.
Yeah. Okay. All right, today is proving to be a long lesson. That happens sometimes, but it's the last one. And we have one thing that we're trying to understand. The biology teachers actually came to the chemistry teachers and said, hey, I heard that you're doing acids and bases. Are you going to talk about buffers? And we were like, no. And they said, well, you should. And we agree with them. Buffers are an important acid-base thingy, and I've actually showed you one already, but I'll show it to you in more detail. They also are wildly important in biology because the existence of buffer solutions in your blood are what are keeping you alive. And we'll get to that in a second, but effectively, lots of chemical reactions rely on really specific pH levels. And for your body to function the way it needs to, your blood always has to be pretty much exactly the same pH. And if an acid or base ever enters your blood and changes the pH, that's real bad for you. And so a buffer is a thing that can help prevent that. So we have a few puzzle pieces that we need to put together in order to explain how and why a buffer works, because it's not immediately apparent, because the easy way to describe it doesn't actually make any sense if you know how acids and bases work. So we have to do it the more difficult way in order to be like, how does a buffer happen? So step 1 is just to gather a few puzzle pieces. The first puzzle piece is basically just review from that video. Water always has both hydronium and hydroxide in it. It's called autoionization. When 2 water molecules bump into each other, there's a possibility that the hydrogen from one sticks to the other one. And as a result, it becomes H3O, and the first one becomes OH minus. That is hydronium and hydroxide. But because 2 water molecules always turn into 1 hydronium and 1 hydroxide, it means in pure water, the concentrations of those 2 things is always exactly the same. Same concentration. While hydronium is what makes something an acid and hydroxide is what makes something a base, if you have both of them in the same concentrations, this still counts as neutral. And then we said in the video, based on the equilibrium point, if you measure the amount of hydronium or hydroxide in pure normal water, the molarity is always going to be 1.0 times 10 to the negative 7 molar. And that negative 7 explains why 7 is given as the pH of anything neutral. Because pH isn't just a made-up scale, it's what happens when you take a real concentration and perform a negative logarithm on it. And so anything that is neutral is going to have a perfect pH of 7. What ion is the acid one? Anything that increases this ion in water upsets the balance and makes it acidic. Which one is that? On the second try, we get H3O+. This is called hydronium. The ion that makes something a base is OH-. That's called hydroxide. Water naturally has both of those, but if something adds more hydronium to the water, it will increase the acidity while also decreasing the hydroxide at the same time, and you end up with more hydronium than hydroxide. If we calculate those things, we can create this pH scale. The pOH scale is what happens if you calculate how much hydroxide is in something and then perform a negative logarithm to that. And it is literally measuring the same thing, but is the opposite of the pH scale. Nobody really uses it because it would be confusing, but like stomach acid has a pH of 1. I like to think of the number 1 acid is the strongest one, and that's how I remember that small numbers are acids. And the really, really big number is a weak base. But if I'm measuring hydroxide instead of hydronium, the stomach acid would have a pOH of 13. So if I said, wow, stomach acid has a pOH of 13, you'd be like, wow, that's a really strong acid. Or if I said stomach acid has a pH of 1, you'd be like, wow, that's a really strong acid. Because those two things mean the same thing, only people mostly don't use pOH because it feels redundant and confusing to have two different scales that are opposites. Yes?
So is it just because they're two different things, like that's why the scales are flipped?
Yeah, because they're measuring different things, but because of the autoionization of water, those two things, the pH and the pOH, reflect one another. If I have neutral water and I add hydronium to it and then do a negative log, then the pH will get smaller and smaller, but the hydroxide will get larger and larger, right? And so because hydronium reacts with hydroxide to cancel one another out, those two numbers always move at the same time in the same ways. But then we measure them opposite because we're looking at different particles. So it's just which particle are you looking at? The other thing, how well did you pay attention to the video? A substance that donates a proton is called what? An acid. After a substance donates a proton, the resulting product is called the conjugate what? Conjugate base. As a result, the one that accepts a proton is a base, and after it accepts a proton, it's the conjugate acid. So if we just use our hydrochloric acid example, acid plus water reversibly forms chlorine ions and hydronium ions. The HCl ends up as Cl because it loses a hydrogen. That makes this an acid and this a base. The analogy I like to use for conjugates is as if the materials are playing a game of catch. At the beginning, the HCl has the ball or the hydrogen and it tosses it to the H2O. So HCl is the thrower and H2O is the catcher. As soon as you're done throwing the ball in the game of catch, are you still the thrower? No, you become the catcher as soon as you finish throwing the ball. As a result, after HCl loses that hydrogen, it becomes the catcher, and so Cl- is the conjugate base, and H3O plus is the conjugate acid. If this reaction were to go in reverse, it would have to be H3O giving the hydrogen back to chlorine. And so an acid always becomes a conjugate base, and a base always becomes a conjugate acid. And the pairs that we care about are the acid and the conjugate base go together as partners. The base and the conjugate acid go together as partners. And that matters as one of the important puzzle pieces for describing what the heck a buffer solution is. The next discussion is going to be probably the most helpful part. If you understand what this is, it's a perfect analogy for what a buffer solution is. So let's reach back and think about solubility. Easy question. Can an infinite amount of salt be dissolved into a glass of water? No, it cannot. What happens to added salt after you reach the saturation point? So we're not talking about supersaturated. That's like a special scenario. If I have a saturated solution, I'm not messing with temperature or anything, and I dump more salt in, yeah, it just sinks to the bottom. All right, so some vocabulary words that can be helpful. If we have like a beaker with some water in it, and I dump some salt inside, some of it will become sodium ions, some of it will become chlorine ions, and the excess will just sink to the bottom as NaCl. There's two different words that we sometimes use interchangeably, but they're technically different. Dissolved and disassociated. Dissolved means really, really well mixed with water. Dissociated means the original particles have broken up into smaller chunks. So the ions up here are dissociated. The stuff that didn't dissolve is undissociated because the sodium is still connected to the chlorine. We want to use that. So here's the part where this analogy becomes really helpful when we get to buffers. If I could somehow take out the dissociated ions, if I could reach in and take out the sodium and chlorine ions up here, what would happen to this system? Like, I take the ions out, what change would you expect to occur? Some of the undissociated salt would mix in. What do you mean when you say mix in? It would probably dissolve, right? So if I take out excess sodium, or if I take out the dissociated sodium or chlorine, some of the excess NaCl would dissociate to replace it. If I continue to take out dissolved sodium and chlorine, would the what would eventually happen? It would all dissolve, and then I would keep taking it out, and eventually I would have removed all of it, right? So eventually, the undissociated salt at the bottom will completely dissolve. And if I keep removing ions, I'll have pure water at the end. If we were to try to graph something like this over time, of me just removing ions, then at the saturation point, it would be really, really stable for a long time, because as soon as I remove particles, new ones can dissolve. And then eventually, it'll do something like that, because right here is where we run out of excess. Is that all pretty clear? Like, that feels obvious that that's how it will work. I tried to dissolve a bunch, it wouldn't all dissolve, I reached the max, so the rest just sank to the bottom. But if I take out the stuff that's dissolved, I am now freeing up the extra at the bottom to dissolve. And so effectively, I've created like a self-replenishing saltwater solution. Whereas as I'm taking out the dissolved salt, it replenishes itself until eventually the junk at the bottom runs out. And so I could get a really stable graph for a long time until I run out of that excess. That's going to be an important analogy. It's not perfect, but it's really close to what makes a buffer solution possible. Now there are two new things we need to describe. One of them is easy and fits our analogy. The other one is weird, but I know I can get you there. Would you rather, if I'm going to throw acid on your face, would you rather I throw a strong acid or a weak acid? Why? Trick question. In this case, the weak acid was really concentrated and the strong acid was super dilute. A strong and a weak acid are not at all what they sound like, because yet again, the lords of chemistry who named the things picked names that are not intuitive. A strong acid does not mean an acid that's really concentrated and good at destroying stuff. A weak acid does not mean an acid that's not very concentrated and bad at destroying stuff. In fact, depending on how you've mixed stuff up, either could be dangerous or not dangerous. The real definitions are a strong acid is any specific species that 100% dissociates in water. Remember, dissociate means breaks apart to form ions. So if I take a hydrochloric acid, which is strong acid, let's say I have 1.0 moles of hydrochloric acid, and I add that to water, so I dump it all into my water, and then I measure how much actual hydronium exists in the water, I would find 1.0 moles of hydronium in the water. Every single hydrochloric acid molecule would have dissociated. If we're going to compare that to what we drew before, we would have something like, here's our water, here's our HCl, it goes into the water, I have H+, I have Cl-, and nothing else. All of it dissociates. The concentration of hydronium is equal to the initial concentration of acid. So what makes a strong acid an acid is usually they are stronger acids because it's really easy to make a concentrated hydronium when all of your acid is providing hydronium. What makes a weak acid usually weaker is something less than 100% dissociates. Vinegar, acetic acid, is HC2H3O2. If I were to drop 1 mole of this stuff in water, and then after it's all dissolved, I measure how much hydronium was actually produced, I would get 0.0028 moles of hydronium. If hydronium is the stuff that makes an acid act like an acid, then mole for mole, the hydrochloric acid is now way more concentrated than the acetic acid, because I started out with 1 mole of each. This one gave me 1 mole of acidic solution. This one gave me 0.0028 moles of acidic solution. It's way more dilute. So the concentration of hydronium we got at the end was less than the initial concentration. The way we could picture this is I have my beaker full of water. I take some HC2H3O2, let's make these clearer numbers, and drop them in. What I will end up with is some H+, some C2H3O2-, and some HC2H3O2. H+ is the stuff that does all the acidy things, which means HC2H3O2 is not able to do acidy things. It's not until it dissociates and that hydrogen comes off that it will behave like an acid. So even though I started out with equal amounts of hydrochloric acid and acetic acid, the top one is a way stronger acid solution because every single HCl that went in there turned into an H+. The bottom one is a much weaker acid solution because only a small handful turned into H+, and the rest just didn't really do anything. Remember, this is all equilibrium based though, so technically at all times, this H plus is occasionally sticking on to that one, and this HC2 is occasionally breaking apart. But it's a lot like when you did the dice thing that favored the carbon dioxide, where these sticking together is or these two sticking together is way more likely than those two breaking apart. So if you roll the dice back and forth, you'll end up with one really full tub of HC2 blah blah blah, and one mostly empty tub of H plus. Does that kind of make sense on what a weak acid is? The main idea is a weak acid is less than 100%. So when you drop it in, you end up with both some dissociated stuff and some undissociated stuff. Which one looks more like our saltwater scenario? The weak acid, right? With salt water, we had some dissociated sodium and chlorine, and because we were intentionally oversaturating it, some stayed undissociated at the bottom. With a weak acid, just by the nature of how it behaves, it has nothing to do with how much you add, you will always end up with some dissociated and a chunk of undissociated floating around. Okay, so now we will get into, well, I guess we could just ask the question. If this reminds us of the salt, if I were to take some of these hydrogen ions out, let's say, for instance, I neutralized them with a base so that the hydrogen ions disappear, what would you expect my undissociated stuff to do? Yeah, to dissolve or dissociate, right? And so you could imagine that this acid could be fairly difficult to neutralize because while it's not very strong, as soon as I get rid of some of these hydrogen ions, new ones could form from all this excess undissolved stuff. So that is one step towards what makes a buffer, a thing where the pH is hard to change.
What if it's a low concentration of acid?
Then it would be a buffer for not very long.
Okay.
But we'll look at that. Okay, here's the last piece. This is a big thing to understand, but I think I have found a way to make it easy if you look at the arrows. Everybody say Le Chatelier. Isn't that a great name? He's some guy. I never pay attention to the history. Le Chatelier was looking at equilibrium, and he was trying to figure out how to explain why equilibrium tends to be self-correcting. I'm going to randomly pull up whoever... Oh, look, Abby Lacey. Your name starts with an A. We're going to see if you put your graph in your notes. Oh, yeah.
I only put one, so.
I only need one.
Yeah, you sent me them. I just didn't like them.
How dare you? Okay. So we did an activity, and I probably, if I did it for your class, showed you what the perfect graph would look like. And it was something like this. I'm going to try to draw it well, where the perfect graph would have done this. Now, does Abby's graph perfectly match the perfect graph?
No, but it's pretty close.
No, but it's pretty close. Here's what's interesting about this. Hi, Abby. Did you know that I have your phone? Because I do. It's right here. I was keeping it in my pocket, but then I sat in my chair and thought, I shouldn't sit on her phone. Okay. Also, I'm recording this. Hi, people listening. All right. Why does her graph... No. Why does... For absent people. I'm recording it for absent people.
You never asked for our permission to
Am I right?
record.
No, it gives me more faces.
Oh my god. Oh yeah, facts. No, you still have to ask for permission.
No, all I have to do is inform you. In the state of Texas, I have to let you know if I'm recording.
Can I decline?
No. You sure can't.
Is
All right.
this for people to do? What is that?
Stop. I have to do chemistry teaching.
Oh, but
Oh,
it's
okay.
gonna be the video, Abby.
All right, here we go. Why was her data able to effectively fix itself when it strayed away from the ideal? Here's why. Let's say right here, you guys clearly had too many blue dice after this particular roll because it's above my made-up perfection line. So what happened? And you didn't control anything, you just rolled the dice and did what the dice told you to do. So why did, after you had too many, the dice immediately plummet down? And the answer is, when you have an increased concentration, you also have an increased reaction rate. And because the increased concentration up here equaled the decreased concentration down here, that means blue is going to react unusually fast the next time, and orange is going to react unusually slow the next time, which means a whole bunch of blues will come down here and not very many oranges will come up here. So you end up with a plummet. In this example, your number was too small, which means this time blue is going to react surprisingly slow and orange is going to react surprisingly fast, and you would normally see it fix itself. Technically, you'll never have a perfectly straight line. You could roll forever and ever, and it would always go up, and then the high concentration would make it come back down, and then the low concentration would make it go back up, and you'll just be dancing around that equilibrium line forever. But if you do it forever and then zoom out, you won't be able to tell that anything has changed. So systems in equilibrium are naturally self-correcting. This is what Le Chatelier was trying to say over here. Oops, in our notes. Where are our notes? Right here. When a stress is placed on a system in equilibrium, like you randomly accidentally get too many dice in your carbon dioxide bin, the system automatically adjusts to relieve that stress. So we're going to just think about a scenario of, imagine you have rolled your dice and you've reached equilibrium. So we're going to use this example. You have around 33 in one bin and around 17 in the other, and you decided to just keep rolling forever, and you're moving the same back and forth, so it's just staying at 33.17. And then I come by and dump a bunch of extra dice into your carbon dioxide bin. What is going to happen? What happens if I increase the concentration of the reactant CO2? What will that do to the system?
It will make the acid weaker.
It will make the acid weaker, which is not true. It will not do that. Decrease the concentration of H2O. So it'll at least temporarily do that, because the carbon dioxide that I add in will react to the H2O. H2O is a little bit of a distraction in this setting because we're talking about aqueous solutions, so we can usually assume there's so plenty H2O going around. But that is true. When the carbon dioxide reacts with the H2O, what will it produce? H2CO3. So ultimately, what will happen to my H2CO3? It will increase. Now there's a vocabulary word that we're looking for. We need to decide, did the equilibrium shift left or shift right? Here's how we figure out the answer to that question. When I added carbon dioxide, what did I do to your forward reaction? If I increase the concentration of carbon dioxide, what happens to the rate of the forward reaction? It increases. We're going to depict that by just making this arrow bigger. When I added carbon dioxide to the carbon dioxide bin, did I do anything at all to the reverse reaction? I didn't. So we're going to leave that arrow alone. So the easiest way to tell that my acid is going to increase is if the formation of the acid, which is my forward reaction, is fast, but the destruction of the acid is slower, what will happen to my total amount of acid? It should go up. Would you call this a shift right or a shift left? It's called a shift right, and the easiest way to visualize that is if I have a real big arrow pointing to the right and a little arrow pointing to the left, then ultimately my equilibrium is shifting right. Which means that this is going to increase When it increases, it's technically going to get faster and faster as it increases until the bottom arrow equals the top one. Let's look at it in the data. So I said I was going to add extra carbon dioxide. You originally had just been sitting at 33 CO2s and 17 H2CO3s. And I come in and randomly add a bunch more so that this says 50. What happens to the actual data? It would look like this. So there's a sudden spike in carbon dioxide because I threw new dice in there. That does not correspond to a change in acid because I didn't do anything to that. Now I have a sudden large amount of carbon dioxide, which means it's going to react more quickly and immediately decrease. The carbonic acid didn't change speed, so it's going to gradually increase until we hit a new equilibrium of about 45 versus 21. Ultimately, I have more carbonic acid than I used to because the equilibrium shifted a little bit. It's still always going to be CO2 favored because that's what the rules do, but I was able to end with a little bit less than the amount that I added, but a little bit more acid. The big piece, the way I want you to think about this mostly is to redo it. We started with, I know that this increased. Because that concentration was higher, it's going to react more quickly. If I'm creating acid faster than I'm destroying acid, the only possible result is that this will also increase.
The acidity will increase, or just the amount of acid will increase?
It kind of depends because if I'm messing with the water as well, then dilution can affect acidity. But in this case, I didn't. So yes, the pH would go down, meaning the acidity was going up because I have more acid particles in the same amount of water than I used to.
And then that would continue until the left formation catches up.
Right. Okay, so you got to figure out the next one. Is this going to be a shift right or a shift less? If instead of increasing carbon dioxide, I sneak by and steal a bunch of dice from your carbon dioxide bin so that this one decreases, what will that do to the equilibrium?
You say no.
Yeah, what do you think?
Shift left.
Shift left. Why did you say shift left?
Said the opposite of the other one.
You said the opposite of the other one. That seems reasonable. Can you explain why a shift left would occur?
Okay, so I think it'd be a shift left just would occur because the H2O is more than the CO2, which is the reactant. Which, yeah, I don't know.
So we need to think about reaction rates. Did I do anything to the rate of the reverse reaction?
Oh, I get what you're saying. Does it take longer for the
Yeah, I didn't do anything to this arrow because I didn't mess with the acid bin. But I did do something to this arrow. What would I have done to it by lowering concentration? Yeah, made it smaller. The way I decided to do that is to take the white one and erase it and then draw a cute little tiny arrow in its place, like that. So before I even ask what's going to happen to the acid, if the arrows are doing this, would they balance out as a shift left or a shift right? Shift left. The faster arrow is going to the left. So this is, gotta go back to my normal boldness. This is a shift left. If my decomposition of acid is faster than my creation of acid, then that means this will decrease until I hit a new equilibrium. Let's look at the data and then answer a question. So what we said is you have 33 and 16 really consistently, and I come by and steal 10 of your dice, so you only have 23 left. What we said is that should result in having fewer acid at the end. And you can see the carbon dioxide takes a huge plummet, and because it decreased, it's still going to react a little bit faster and increase. the acid is going to react a little bit slower, and it ends up in a balance of like 13.5 rather than what we had started out with at 17. If one way to decrease the acid content in this particular system is by, instead of removing acid, I could remove carbon dioxide, and due to Le Chatelier's principle, the amount of acid will also be reduced. Good so far? Grace, you had a question?
So this reaction is making an acid, like CO2 plus H2O makes H2CO3 the acid?
Yeah.
Okay. But, okay, sorry, I was just getting confused because I thought we were talking about the ones where like it steals the hydrogen and then the one that gave the hydrogen was the acid, but this is different.
Yeah, I mean, this is slightly different.
Because the ones on the left aren't acid based, the one on the right is just acid.
Yeah, if we so this is a synthesis reaction of carbon dioxide plus that forming a different acid. You could write a completely different reaction where you say, how does H2CO3 react with water, and it would do the whole thing like that, where that turns into H and that turns into H3O. But yeah, this is just describing a general synthesis chemical reaction so we can figure out equilibrium. Yes?
Do we not like really know what happens to H2O?
Well, so the H2O is sticking to the carbon dioxide. And so technically, if I have less carbon dioxide, but the H2CO3 is still breaking into those two things, then that would technically be increasing in this scenario until we hit equilibrium. That's not something that we track as consistently because we usually don't care how many water particles are in something. We care about what's in the water. But if H2CO3 is, I mean, like if I have CO2 and it sticks to H2O, then this particle is the H2CO3. It's a really convenient chemical reaction because literally those two things just stick together, and we call it that now. And so if this breaks apart, it would break apart into these two things. Oh, I failed. But you see, it was the carbon dioxide and water. And so technically the total amount of water does go up because less of it is being used up by the carbon dioxide. Last one. If I sneak by your desk and I increase your amount of acid. So you're rolling your dice, you've reached equilibrium, and then I sneak a bunch of extra dice into the acid container. What is the result going to be?
The other ones will increase also.
Which ones will increase?
CO2
CO2
and H2O.
and H2O. Why do you say that?
Because when the reverse reaction happens, there will be more CO2s and H2Os that break apart.
Right? So by adding more acid, I have increased this reaction rate to make it extra big. That looks ugly. But I haven't done anything to increase the forward reaction. So this is a shift left again. That should result in more total carbon dioxide and water. If we go test that against our model, we'll undo that last change. We said I hit equilibrium at about 30 and 16. If I randomly add more, I'll change this to like 30. We hopefully will see more than 33 carbon dioxides at the end. I hit go. The whole thing shifts, so now I have 41 carbon dioxides. In equilibrium, if you mess with it, it's always going to go find equilibrium again, although that the exact number of particles will change, especially if I'm changing the number of particles. Okay, so that's Le Chatelier. Here's what we've done so far. We have said that water always contains both hydronium and hydroxide. We've said an acid is sometimes going to work together with its conjugate base to accomplish something. So it's important to be able to figure out what a conjugate base is. And we have said solubility can be, or saturation can be sort of stagnated if I have a bunch of extra undissolved stuff at the bottom. Then we said a weak acid can act a lot like an oversaturated solution where you technically have undissociated stuff. And then we said Le Chatelier's principle explains how a weak acid could be possible, because it's basically if this represented our weak acid, where the top number is the acid and the bottom number is the actual hydronium that's coming off of it, then when I come over and randomly take some acid away, so like I turn 34 down into 30, the hydronium stays close to the same. It decreases a little bit, but it doesn't decrease as much as my original decrease, because it is the equilibrium allows it to be reestablished. It responds to fix the problem that I changed. Okay, we're finally ready to talk about what a buffer is. A buffer is a solution carefully designed to resist pH change. I already showed you a buffer solution, but I'm going to do it just a little bit better because it works better in a beaker than in a graduated cylinder like I used last time. So look, here's some water. There's a little magnet inside, which means when I do this, I can stir the water automatically, which makes like a fun little tornado. Here's my indicator dye. If I put my dye into pure neutral water, what color should it turn? If you don't remember, you can scroll up to look at the pH scale on your notes. Green. I need more green. Perfect. This tells me that, it doesn't tell me that there's no hydronium or hydroxide. It just tells me that there are equal amounts of hydronium and hydroxide, so they're canceling each other out, and none of them are able to change the color of that. If I take sodium hydroxide and I add extra hydroxide particles to this, what will happen to the color? If you don't remember how the indicator works, you can scroll up and look at your pH scale, because the colors on that scale match the indicator. I'm going to add extra hydroxide. Yeah, it should go bluey purple. Ready? Here we go. So what just happened is there was a chemical reaction. This dissociated. The hydroxide reacted with the hydronium that's already in there to decrease it, and then the leftover hydroxide just hung around. So now I have more hydroxide than hydronium, and that is called a base. An Alka-Seltzer is an acid. If I add an acid to a base, what should happen? Right? So the hydronium in my Alka-Seltzer will react with the hydroxide that's in there, canceling it out. If this were exactly the same amount as that, it would turn green. If it's less, it'll be just less blue. If it's more, it'll go past green into like yellow or red. Ready?
Look at the red. It's more. Oh, it looks like a tornado.
Yeah, it's stirring.
What?
Is this in the way? It takes a while for it to finish reacting.
It's going back to green.
Not in the tornado.
All right. So we're like kind of greenish now that it's finished reacting, but this is definitely still on the yellow side. So we have a mild acid right now. So that means I added a little bit more hydronium than the amount of hydroxide that was in there. I canceled out all of the hydroxide and then kept going a little bit to make an acid. If I wanted it to turn green, all I would have to do is add more hydroxide, right? If I could very carefully add just a little bit of hydroxide, I should be able to get it back to neutral. Want me to try? Okay, you ready? Oh, I did too much.
Oh, Mr. Boy.
Except I didn't. Notice how it didn't change color even at all.
It's because the sulfur.
Alka-Seltzer is a buffer. It resists pH change. This is yellow, which is just barely acidic. If I add almost any amount of base to it, it should go down into green or even blue. But instead, it tries to turn blue and then comes back up to yellow. What is happening?
Is it like the thing where you those stomach acid tablets where it released a certain amount of the base? If there was too much acid, like release base, you get back to neutral.
It's like that, but it's a chemical reaction. There's nothing like physically happening. We're going to talk about it. This is slightly acidic. If I add more acid to it, it should become more acidic, right? What color is more acidic? Red. So if I add some hydrochloric acid to it, nothing. It was red for like a second. Nothing. A buffer resists pH change. The way that you make a buffer is by combining an acid or base with its conjugate pair. So just looking at this real quick, effectively we're saying the Alka-Seltzer has an acid and a base in it, which means if I throw my sodium hydroxide in there, instead of changing the pH, it just cancels out the acid in my Alka-Seltzer. If I throw an acid in there, instead of changing the pH, it just cancels out the base in my Alka-Seltzer. What is wrong with my explanation that I just gave? An Alka-Seltzer is an acid and a base.
So it cancels out this.
So it's just water.
So why does water not act like this, right? So the big confusing question is, if supposedly an Alka-Seltzer works by containing both an acid and a base, why don't that acid base just cancel each other out and stop doing anything at all? That's where we have to figure things out. Is it because they're what?
Not reacting.
Yes, but why aren't they reacting? Like, a defining quality of an acid and a base is that they react with one another. So in order to create a buffer solution, we have to figure out how to get an acid that will neutralize bases and a base that will neutralize acids, but the acid and base can't neutralize each other. Here's exactly how you make it. One example of an acid would be, or of a buffer, would be combining acetic acid, which is a weak acid, with its conjugate base. So what is the conjugate base? Here is our acid formula for turning acetic acid, or how acetic acid reacts with water. Let's identify the acid, base, conjugate acid, and conjugate base so we know which two things need to be combined to make the buffer. So what is the acid? Which one is donating the hydrogen? Right? So the hydrogen must be moving from here to there because that's how it becomes H3O. So this is my acid, which makes this my base. We said we want to combine the acid with its conjugate base pair. So on the right side of the equation, which one is the conjugate base? The conjugate base is the one on the right side that is able to receive a proton, able to accept a proton. So this must be the conjugate base, meaning this is the conjugate acid. So the ingredients that I need to make the buffer are the acid and the conjugate base. Because C2H3O2 is an ion, you can't just get a bottle of acetate ions. You have to get blank acetate. So one example might be sodium acetate, but it doesn't matter. That first thing will just be a spectator. All I need is the acetate. If I can combine vinegar, acetic acid, with anything that provides acetate ions, I will create a buffer. The reason why this acid doesn't react with the conjugate base is because it's a product. It's not going to react with the product of itself. So by the nature of using things from two different sides of a chemical equation, these two will not react with each other. So how do they function to stop acids and bases from changing the pH of something? The short version is these two things won't react with each other. If I add extra hydronium, then what will happen is this hydronium will react with the conjugate base and basically get a hydrogen attached to it so that I have less conjugate base but a little bit more of my weak acid. If instead I have hydroxide in there, then the hydroxide will steal this hydrogen and I will have less weak acid but a little bit more of my conjugate base. Does the little chart make sense so far? Rather than the hydronium or hydroxide changing the pH, they are going to stick to these things and neutralize in a way that doesn't change the pH. But we need to talk about how that's possible. Why do I have to use a weak acid for this to work? You might need to scroll up and look at the analogy we made when we discussed the weak acid. So if I use a strong acid, it is 100% dissociated. And so let's say, for example, that I have HCl. It's going to turn into H plus and Cl minus, which is great. If I drop like a base in here, though, it will react with those guys and use them all up, and so it will become more basic. How is a weak acid different?
It's already off, or it isn't already off.
A weak acid is not all the way dissolved. So if I use something like HC2H3O2, one way to think about its dissociation is it turns into H plus and C2H3O2 minus and leftover H C2H3O2. So if I have all three of those things in my solution, then when I put some hydroxide in there, it will cancel that out. But as soon as that gets canceled out, Le Chatelier's principle says this now has room to turn into this. C2H3O2 minus. Do I have less hydronium than I used to? No. So the weak acid acts like excess salt in our saltwater analogy. When H plus gets neutralized by OH minus, the undissociated acid will dissociate to replace the H plus. So that's why I like the saltwater analogy so much, is because it's so clear, like you can see it and you can feel it. With this, we couldn't see what was going on. I probably have messed with it too much, but I'll try one more squirt of blue. This is yellow because it has an excess of hydronium. That's what makes it acidic. If I add a little bit of hydroxide, the hydroxide will react with the hydronium to neutralize it. So it tried to go green and then it came back to yellow because after neutralizing the excess hydronium, the weak acid that I have in there from the Alka-Seltzer was able to dissociate and replace the hydronium that I lost. That's why it stayed yellow. What keeps it from changing in the opposite direction? I have to use a conjugate base, not a regular base. Why? Do what? Right. A conjugate base will not react with the original weak acid because it's a product. However, it can neutralize added H plus by what's the word I'm looking for? Accepting it as accepting it to form more weak acid. Hydrochloric acid is a strong acid. It dissociates very quickly and adds a whole bunch of hydronium to the list. But if I've got a whole bunch of acetate in here, if I have a whole bunch of conjugate base, then when I add hydrogen ions, those hydrogen ions will quickly stick to the conjugate base and turn into weak acid. Weak acid is more likely to be undissociated than dissociated. And so I don't get to keep those ions. And so here's our last question. What would cause our buffer solution to fail? Think about the saltwater thing.
Too much.
Too much what?
Too much of something.
It's actually too much of anything. If hydronium ions are causing this to gradually decrease, eventually it will decrease enough that I don't have any more. It runs out and new hydronium ions will just turn it into an acid. If hydroxide ions are causing this to gradually decrease, if I do it too much, I eventually overwhelm it and it will become basic. Do you want me to turn it red or blue?
Red.
I heard red. So all I have to do is pour in acid until all of the conjugate base gets used up, and then any additional acid I pour in will just dissociate and it will become more acidic. Not there yet. Still not there. I'm gonna have to mix up more of my acid. We're getting closer. You can tell when it takes longer and longer for the color to shift back, it's because my concentration of conjugate base that's counteracting this is getting lower, so it has a slow reaction. At this point, I'm pretty sure that I'm most of the way there. And there we go, we overwhelmed the buffer. Now, if I add acid or base, the buffer is gone, and it should just change colors every time I add stuff. Let's add some more base just for fun. We should see it quickly change colors instead of resisting. There, it took us back into yellow. Does that make sense? Let's turn it blue. Blue is fun. Ooh, green. Blue. Our indicator's fun. Okay, we have like 10 minutes left. We're going to talk about blood super briefly. Your body has a pH, your blood has a pH of 7.35. If the pH of your blood changes by 0.4, you could die. Which means a pH of 6.9 could kill you. A pH of 7.7 could kill you. Things like alkaline water are mostly pointless. Because your body is like trying to maintain its own certain pH, and if you're messing with your pH on purpose, your body's going to resist it. You have a buffer in your body that's causing it to actively fight against any weird changes you make. So the specific buffer in your blood is a mix of carbonic acid and the conjugate base bicarbonate. So let's say something goes crazy and you end up with excess H3O plus in your blood. that will quickly react with the HCO3 minus to produce. Hydrogen comes over here. You end up with regular old safe water and H2CO3. H2CO3 is a weak acid, so it mostly won't dissociate, which means the excess hydrogen ions that are trying to kill you are basically getting absorbed into this weak acid. If the reverse happens and you have too much base in your body, fortunately, you also have a weak acid. The extra hydrogen from this will be absorbed over there, and you end up with regular, safe water and the conjugate base bicarbonate ions. Your body is just going to continually produce these things, so you can't ever run out. And as a result, it takes an enormous amount of acid or base in your body to change anything. Now, this is where it would be a good idea to stop because, like, class is almost over and I can tell you're tired. But your homework asks you to do a thing, so I need to teach you how. It'll be real fast and easy. We're only going to look at 2 examples unless you want more.
Get rid of those.
I just want to do 2. Those are both strong. I don't care about strong. I only care about weak. If I asked you that to make a buffer, let's say I said, hey, you have the base baking soda. How would you make this into a buffer? Well, you have to have a base and its conjugate acid. So you need to be able to identify what the conjugate acid would be that goes with this base. This is weak. It can't happen with strong ones. So the 2 things that you need to know is way at the beginning when we were talking about finding a conjugate acid, we said we don't really care about the metal. We just care about the ion that it's giving us. So my active ingredient is HCO3 minus. I know that it has a minus because I'm ignoring that positive sodium that I crossed out. The sodium isn't actually participating in acid-base chemistry. It doesn't affect the what am I looking for? The movement of the hydrogens back and forth. Okay. It was just providing this guy that does. So if you have a base, it's usually going to involve, so if you had Tums down there, you would cancel out the calcium. Is a base a proton acceptor or a proton donor? A base is a proton acceptor, so let's have it accept a proton. And what does it turn into after it accepts a proton? H2CO3. This is the conjugate that I have to combine with baking soda. If I get baking soda and carbonic acid, I now have a buffer solution.
So is that why, like, whenever you make slime and you, like, mix something up with baking soda, it, activates the slime?
I don't know what you're putting in your slime. Oh, I don't really know what borax is. I gotta look that up. One last thing. I want to do an example with acid. If I gave you, hey, come back to me. We're almost done. If I gave you lemon juice and said, I want you to turn this into a buffer solution, what would you do? Well, this is an acid. That's not the word acid. This is an acid, and so I need to know what conjugate base to add to it. So I start out with my acid, H3C6H5O7. Is acid a proton donor or a proton acceptor? Donor. So that means this thing will be getting rid of some number of protons, probably all of them. The only reason I wrote 3 is because it started out with 3 hydrogens. After it's done donating its protons, what's left? C6H5O7 with a -3 charge because that's how many protons it lost.
So it just always
What's the
serve all
difference
of the
between
protons.
H3 and H5?
We can talk about that in just a second. You want to get rid of the ones at the front. So the conjugate base that goes with this acid is going to be whatever you call C6H5O7. If you wanted to make a buffer solution out of lemon juice, you would need some lemon juice and something else that has C6H5O7 in it. And then to conclude, I'm just going to answer Abby's question. The hydrogens, the reason hydrogen is written in there twice is because the ones on this side are more strongly covalent in this structure than the ones on this side. So when it dissolves, all of these guys are going to stay stuck to the carbons and stuff, and those ones are going to float around. Yes?
Okay, so this is a previous question. How does